Analytical Chemistry 1, Lesson 14. So far, we have been looking at statistical tests that focus on the values of the means. It turns out that the distribution of the data points is an equally valuable way to analyze data sets. We want to look at another valuable statistical test, the F-test. First, a little history. As you get deeper in statistics, you will come across two names quite a lot, Carl Pearson and Ronald Fisher. They were two of the leading statisticians working at the end of the 19th and into the first half of the 20th century. You will find their names associated with many different statistical tools. The F-test we are about to study is the Fisher test. Now, by the way, the T in t-test stood for test, as in the test statistic. We want to look at the F-test. First, a little review for context. Recall that we were able to use the Z-statistic test when we assumed that the errors were distributed normally, that is, according to a Gaussian function. We looked to compare the fraction of the integral under the curve that was represented by our data to that fraction that was excluded to determine probabilities and confidence intervals and to determine if we could reject or fail to reject the null hypothesis. Gossett showed how this had to be changed when small numbers of samples were involved and created a new mathematical form called the t-distribution. The same arguments regarding the integration under the curve is made as for the Gaussian function, except that the t-distribution functions differ with the degrees of freedom and they are wider than the corresponding Gaussian. Now, the Fisher test uses a completely new function for the probability distribution. Its most obvious feature is that it is no longer symmetric around the center line, as is the case with Gaussian and t-distribution functions, but it is used in a similar fashion by looking at what the fractional area under the curve, where it's found for certain integration limits. The b represents the beta function with the two parameters d1 and d2, and x is the continuous variable. As with the t-distribution, the function's shape changes with different values for the parameters, the values of d1 and d2. They too are degrees of freedom. There are many different tests that can be done with the F-distribution, just as there were with the t-distribution, but we will focus on just one. We use the F-test to compare two data sets to see if they are statistically the same, to see if they come from populations with the same population variance. Calculating the F statistic is very easy. It's just the ratio of the sample variances for the two data sets we are comparing. Place the largest variance in the numerator so that the value of the F statistic is always greater than 1. We choose a one or a two-tailed test. We decide on a probability level at which we will test the two variances, and we need to know the degrees of freedom for both sets of data. The null hypothesis for this test is that the two data sets have the same population variance. Now, note carefully how I use sample variance and population variance in this section. We use the sample variances to form the F statistic, but the test is whether or not the samples come from populations with the same population variance. In a one-tailed test, the alternate hypothesis is that the variance of the first set, the one on top, is statistically larger than that of the second. This would imply that the second set of data is more precise than the first. It has a smaller variance. In a two-tailed test, the alternate hypothesis is just that the two sets are different. We compare the calculated F statistic with the value from the F table, which is chosen based on the degrees of freedom in the two data sets and the desired probability level. F tables can be very extensive. Here's a simple one. An entry is found by identifying the column with the correct degrees of freedom for data set 1, the one on top, and the row corresponding to the degrees of freedom for data set 2, the one on the bottom of the F statistic. Look at the bottom in the instructions and you will see that this table is for one-tailed tests, and the title tells us that it is only for 95% confidence. Excel has a function to find the values for any degrees of freedom at any confidence level. The function is f.inv, with the probability at the critical value with the degrees of freedom for the first and then the second data sets. For example, here at the 95% level, with the first data set having 10 degrees of freedom and the second set is 13 degrees of freedom, Excel gives the value 2.671 for the F statistic, which is what we find in the table. And by the way, since the sample variances are different, this function is not symmetric with respect to the degrees of freedom. So be sure to get it right. Most of your work will be with the one-tailed test. but it can be used for a two-tailed test. Then the alternate hypothesis is that the two distributions are different, without a claim to which one. Because the f distribution function is not symmetric in the way that the Gaussian function and the t distribution functions are, you can't just change the sign. Use the f dot in function for 1 minus the probability value to get the lower value, and don't forget that you are now excluding twice that probability, same amount on the left as on the right. Perhaps it's best to look at some examples. Chromium metal can be a serious contaminant in the environment. The site of a former manufacturing facility, a tannery in this case, is thought to have soil that is contaminated with chromium. You have two instruments that are available to analyze for chromium, an atomic absorption spectrometer and an inductively coupled plasma atomic emission spectrometer. We will abbreviate them as AA and ICP. There are other ICP experiments, such as coupling the output to a mass spectrometer, but for here, we would just call the spectroscopy experiment ICP. To collect the soil, you collect the soil and extract the metals by washing it with acid. You take 20 samples and divide them into two groups of 10 and analyze each group with either the AA or the ICP. Here are the results that were obtained. The AA experiment does have a larger variance, which suggests it is less precise. Now remember that this statistic is working with variance and not standard deviation. The null hypothesis claims that the difference between the two experimental techniques that we are seeing is just a result of statistical variability and that the two experiments are inherently equivalent. The alternate hypothesis is that, we are taking a one-tailed test here, is that the difference is real, that the AA experiment does come from a population with a larger population variance than for the ICP. The ICP really is a more precise experimental technique, at least under the conditions being studied here. Can we reject the null hypothesis with 95% confidence? Now remember that this is based on the degrees of freedom for each data set. Both sets used 10 samples, so the degrees of freedom for each is 10 minus 1 equal to 9. So, by the use of an F-table, or by going to Excel, we find that the F-inv 0.9599 is equal to 3.179. This is the critical value to consider. It means that there's only a 5% probability that an experimental F statistic will have a value greater than this value and still have the null hypothesis being true. From our data, we find the calculated F statistic to be 3.875. The calculated statistic is greater than the tabulated one. This means that we can reject the null hypothesis with 95% confidence. We can infer from this that the larger variance, and therefore the standard deviation in the AA experiment, is more than just statistical variation, and we will get better results using the ICP-AES experiment. So we head back to work with just the ICP and find out how widespread the chromium contamination is. And by the way, the maximum acceptable concentration of chromium in drinking water is 100 ppm in Canada. This was recently increased from 50 ppm, which was the level set in 1986. We are just looking at the soil for now. We would, at some point, need to examine the groundwater as well. Now, here's an aside. If you read Health Canada's current document on chromium in drinking water, you will find the mass spec version of ICP being by far the most sensitive instrumental technique, with several ICP AES and AAS methods vying for second place. And so, a second experiment or example is that to consider the runoff of pharmaceuticals into municipal wastewater streams. This is becoming the next big challenge for water treatment plants. You're starting out and you want to test different techniques, and your first technique is a simple titration. So you create an aqueous solution by dissolving some acetaminophen Tylenol tablets in water. You create 10 small aliquots of the solutions and titrate 3 of them to get this data. Then you sneezed, just as you were holding the burette. It broke, and you could not get a new one until the next day. So you get a new burette the next day, calibrate it, and then complete the last 7 titrations to obtain this data. Now, the null hypothesis would claim that there is no difference between the two, and you can just lump them all together. The alternate hypothesis suggests that they are different, that sigma 1 squared does not equal sigma 2 squared. Here are the data from each day along with the sample average and sample variance for each. Here we calculate the F statistic from our data and use Excel for the 95% confidence critical value, f.in 0.9562. It's equal to 19.330. Now remember to get the correct number of degrees of freedom and be careful to put them in the right place in the argument list. The critical value is much greater than the experimental value when treated as a one-sided test. It suggests that there is no difference between the two data sets, so you can combine them and treat them as a single data set. We could have treated this as a two-tailed test at the 95% level. Then the two critical values would be, now remember we now need 2.5% above and 2.5% below, 39.33 and 0.1377. If the experimental F statistic lies between these two values, then we cannot reject the null hypothesis, which is clearly the case here. The results for the lumped together data is here. We find the standard error from the standard deviation. We divide it by the square root of the total number of statistics, which is now 10 because we've put the two data sets together. We obtain 95% confidence limits. We find the t statistic in Excel. We want the two-tailed value since we're finding both the upper and lower confidence limits to form a confidence interval. T.inv.2t at 0.05 and 9 is 2.2622. With 95% confidence, the true population mean of the concentration of acetaminophen will be in the interval 1.4 millimolar to 1.55 millimolar.